Have you ever thought about, like, what truly sets us humans apart? I mean, you really thought about it.
Oh, there's a lot of things. I mean, creativity, art, even our complex emotions. But
But one of the most fundamental things is our ability to reason, and more specifically, our capacity for mathematical reasoning.
you're absolutely right. And it's not just about doing calculus or solving equations. It's about the underlying logic that shapes how we think, how we understand the world, how we make decisions, everything.
So today, on this deep dive, we're taking a journey into the very heart of mathematical reasoning. We're going back to the absolute basics.
Yeah.
And I have to say, the material you've dug up for us is, well, it's really fascinating. It starts with something that seems deceptively simple: statements, the very building blocks of mathematical thought.
Yeah, and the cool thing is that not just any sentence you utter or write down qualifies as a mathematical statement. It has to meet very specific criteria to make it into the world of math.
And that's what we're going to unpack today. The sources also mention two key approaches to reasoning in mathematics: inductive and deductive. For this deep dive, though, we're going to focus solely on deductive reasoning.
Exactly. That step-by-step logical process of starting with general principles and then using them to arrive at specific, undeniable conclusions, it's truly the bedrock of mathematical certainty.
And it's interesting to note that this isn't some newfangled idea. The sources even point back to George Boole in his 1854 work, The Laws of Thought, which laid the groundwork for a lot of the formal study of logic.
It really was a pioneering work in the field, so ready to dive in.
Absolutely. Let's tackle the first big question. What in the world makes something a genuine mathematical statement? What's the strict definition?
The key here is absolute precision. A mathematical statement, a true one, has to be definitively either true or false. And there's absolutely no room for ambiguity, no middle ground whatsoever.
It has to be one or the other, no matter what. Our sources give some great examples. Like, in 2003, the president of India was a woman. We can check the facts. In this case, it turns out to be false.
But even though it's false, it still fits the definition of a mathematical statement because it is definitively one or the other. It has a fixed truth value.
Right. It has that clear-cut, true or false quality.
Yeah.
And same goes for an elephant weighs more than a human being. Again, pretty clear-cut, it's true, and it fits the bill of a mathematical statement.
Right. It's straightforward. Now think about this one. Women are more intelligent than men.
Ooh, a bit controversial.
Yeah, but that's exactly why it's a perfect example of something that is not a mathematical statement.
How so?
Because it's inherently ambiguous. What do we even mean by intelligence? How are we measuring it? Are we talking about emotional intelligence, IQ scores, creative problem solving, or something else entirely?
Right, there's no universal agreement on any of that.
And that's precisely the problem, because there's no universally agreed upon way to definitively prove that statement true or false for all cases. It doesn't pass the test of a mathematical statement. You see how this strict definition helps to prevent these kinds of endless subjective arguments? It brings in that essential element of objectivity.
Totally. It removes opinions and feelings from the equation, so to speak. Okay, so factual statements, even if false, can be mathematical statements. What about sentences that use variables, like the sum of x and y is greater than 0? That could be true or false, depending on what x and y are.
Exactly. On its own, like that, it's not a statement because it depends entirely on the specific values you plug in for those variables. In some cases, it would be true. In others, it would be false. However, if you add something called quantifiers, it changes the game.
Quantifiers.
Yeah, those are words like for any or there exists. If you said for any natural numbers x and y, the sum of x and y is greater than 0, well, then you've transformed it into a statement.
Because now you're saying it applies to all natural numbers, not just specific ones. And in this case, that statement would actually be true.
Precisely. You've eliminated that dependence on specific values and made a universal claim. So it's the addition of these quantifiers that turns it into a proper mathematical statement. Now, what about other types of sentences we use all the time, like exclamations, how amazing, or commands like, think about this?
Those definitely don't feel very mathematical.
And you're right. Those, along with direct questions, are not considered statements in the world of mathematical language. An exclamation is expressing an emotion. A command is an instruction. A question is seeking information. None of them make a definitive claim that can be judged as definitively true or false. They don't have a fixed truth value.
They're all about feelings, actions, or missing information. They're not making a clear claim about something being definitively one way or the other. Makes sense. Now, the sources also talk about sentences that use variable time or place. Like they mention words like today or here. Why don't those usually count as mathematical statements?
because their truth can change depending on when or where they're said. Take tomorrow is Friday. If you say that on a Thursday, you're spot on, it's true. But say it any other day of the week, and well, you're wrong, it's false.
Right, so the truth of the sentence hinges entirely on the context, on the day it's spoken.
Yeah.
And that context isn't fixed within the sentence itself.
Exactly. The same principle applies to pronouns like she or vague references to location like there, unless you have a very specific and agreed upon context. It all boils down to whether the truth value is fixed or not.
But there's a super interesting exception to this in the material, right? Something like, there are 40 days in a month.
Yes. That's a really clever example because even though it's talking about a variable time, any of the 12 months, the statement itself is always false. No month has 40 days.
So because its truth value is fixed as false, it does qualify as a mathematical statement. So interesting.
Isn't it? It's the unyielding, fixed truth value, even though it's false in this case, that makes it a mathematical statement.
That's such a subtle but important distinction. So it's not just about a sentence potentially being true or false under certain circumstances, but whether it is consistently one or the other, no matter what.
You got it. And the sources really emphasize that the reasoning behind why a sentence is or isn't a statement, that's what's really important. They even give us an exercise with a bunch of examples, like there are 35 days in a month, which is false, making it a statement.
Versus mathematics is difficult, which is totally subjective, so not a statement.
Right, or how about the sum of 5 and 7 is greater than 10?
True, so it's a statement.
And then there's answer this question, which is obviously a question and not a statement at all. It's not making a truth claim.
So it's the reasoning behind the answer, not just the answer itself, that really helps us understand the nature of mathematical statements.
Absolutely, it's all about the why. Now, to make things a bit easier when talking about these statements, mathematicians have a sort of shorthand, right?
Right. They use lowercase letters like P, Q, and R to represent entire statements. So instead of writing out the square root of 2 is an irrational number every time, you could just say, let P be the statement, the square root of 2 is an irrational number.
Precisely. It's a way to make discussions about logic and reasoning much more concise and easier to follow. Mathematicians are all about efficiency. So we've got our building blocks, these mathematical statements that are either definitely true or definitely false. Now, how do we start building more complex structures from these? How do we manipulate them to form new ideas?
Well, our sources dive into a few key ways to do just that. The first one they introduce is negation.
Ah, yes, negation. Essentially, it's the art of denial. It's taking a statement and saying, nope, that's not true.
So if we have a statement, let's call it P, its negation, which we can write as tilde P or just say not P, is basically the opposite of P.
Exactly. So if P is New Delhi is a city, which is a true statement, then not P or tilde P is New Delhi is not a city, which would be false.
But what's really cool is that our sources point out that understanding the negation of a statement can help you understand the original statement even better.
It forces you to think about its boundaries, its limits.
They give this example. Everyone in Germany speaks German. To negate that, you have to be really careful about what you're actually saying. It's not no one in Germany speaks German, but rather not everyone in Germany speaks German.
Which just means there's at least one person in Germany who doesn't speak German. It highlights that subtle but important difference.
Right. It's about pinpointing exactly what the statement is not claiming. So the negation hopes to clarify the scope of the original statement. The sources also walk us through a few more negation examples. What about this one? Both the diagonals of a rectangle have the same length. What's the negation of that?
The negation would be there is at least one rectangle whose two diagonals do not have the same length. It only takes one counterexample to disprove a statement that claims something is true in every single case.
And what about a simpler one, like 7 is rational?
The negation of that is simply 7 is not rational.
Straightforward enough. The sources then give us a bunch of statements and ask us to both negate them and say whether the negation is true or false. Like Australia is a continent is a true statement, so its negation, Australia is not a continent, is false.
Exactly. That one's pretty simple. Let's try this one. There does not exist a quadrilateral which has all its sides equal.
Well, that's actually a false statement, right? Because a square has all sides equal.
Exactly. So its negation, there does exist a quadrilateral which has all its sides equal, is true.
Okay, cool. Then there's every natural number is greater than 0. It's a true statement, so its negation. There exists a natural number which is not greater than 0. Must be false.
You're getting the hang of this. And how about the sum of 3 and 4 is 9?
Well, that's obviously false. So the negation, the sum of 3 and 4 is not equal to 9, is true.
Perfect. So, as you can see, Understanding negation not only gives you a new statement, it also helps to reinforce that key principle we discussed earlier, that every mathematical statement has to be definitively either true or false. There's no wiggle room.
Right. It really drives that point home. Now, the sources also encourage us to play around with pairs of negations, which I think would be a fun exercise for anyone listening who wants to really test their understanding. But let's move on to another fundamental way we can build more complex ideas from those basic statements.
And that is by combining them.
Exactly. And that's where we get into compound statements and connectives.
Right. So far, we've been dealing with single, standalone statements. Now we're going to link them together to create more intricate ideas.
And the two most common connecting words or connectives are and or.
Exactly. The sources give us the example. The sky is blue and the grass is green. That's a classic compound statement. It combines two individual statements. The sky is blue and the grass is green, linked together by the connective and.
Another one they give is 0 is a positive number or a negative number, where the component statements are 0 is a positive number and 0 is a negative number, and they're linked together by or.
Right. And then they dive into a bunch more examples, like a square is a quadrilateral and its four sides are equal, where both parts of the statement are true.
And then all prime numbers are either even or odd, where both parts are false.
Then there's Chandigarh is the capital of Haryana and UP, which is a mix. The first part's true, the second part's false.
And 2 is a rational number or an irrational number. First part's true, second part's false.
And lastly, 24 is a multiple of 2, 4, and 8. All three parts of that one are true.
So lots of different combinations there. But the key takeaway is that compound statements let us express these more nuanced mathematical ideas by linking together those simpler statements.
Exactly. But here's the thing. The truth or falsity of the whole compound statement depends entirely on the truth or falsity of its individual parts and on that connective that's holding them together.
Right. It's all about how those pieces fit together. Let's zoom in on the connectives themselves, starting with and. What's the rule for when a statement using and is considered true?
The rule for and is pretty strict. A compound statement using and is only true if every single component statement is true. If even one of those parts is false, the whole thing is false.
So it's like a chain. If one link breaks, the whole chain falls apart.
A perfect analogy.
Okay, so that means a statement like a line is straight and extends indefinitely in both directions, you're true because both parts are true.
Exactly. But rho is less than every positive integer and every negative integer is false. Even though the first part's true, the second part about negative integers is false. So the whole statement is false.
And all living things have two legs and two eyes is false because both parts are false.
Right. Now, the sources also mention that we have to be careful not to confuse the logical and with how we sometimes use and just to list things. Like in the phrase, a mixture of alcohol and water and is just connecting nouns, not making a truth claim. It's just describing ingredients in a list.
Okay, good point. Don't get tricked by everyday language sneaking into our logical world. Now on to the other big connective or. That one seems a bit more slippery.
It definitely can be. The word or has two different personalities in everyday language. It can be inclusive, meaning it's true if one or both parts are true, or it can be exclusive, meaning it's only true if one part is true, but not both.
Oh, I see what you mean. Can you give us some real-world examples?
Sure. Think about, to enter a country, you need a passport or a voter registration card. In most cases, that's an inclusive or. You can enter if you have a passport, a voter registration card, or if you're super prepared and have both.
Right. Either one or both works.
Now contrast that with two lines in a plane intersect at a point or are parallel. That's usually an exclusive or. They can't do both at the same time in standard geometry.
Ah, okay. So when we're talking about or in the logical mathematical sense, which one do we usually mean?
In the world of math, we usually assume the inclusive or unless it's explicitly stated otherwise. That means a statement with or is true if at least one of its parts is true. It's only false if both parts are false.
Okay, so two lines intersect at a point or they are parallel would be true because at least one of those things has to be the case.
Exactly. And how about 125 is a multiple of 7 or 8?
Well, neither of those is true, so that whole statement is false.
Spot on. And the school's closed if there's a holiday or Sunday is true because the school would be closed in either of those situations, or even if both a holiday and Sunday happen to coincide.
Right. And what about Mumbai is the capital of Kolkata or Karnataka?
Mumbai isn't the capital of either state, so that one is definitely false.
False. The sources give us another exercise where we have to figure out if the or is inclusive or exclusive and decide if the whole statement is true or false. Like, 2 is a rational number or an irrational number. I think that's exclusive, right?
Yes, it is. A number can't be both rational and irrational at the same time, and the statement is true because 2 is indeed a rational number. How about this one? To enter into a public library, children need an identity card from the school or a letter from the school authorities.
That feels inclusive because a child could have both, and either one would probably work. And that statement is likely true in practice because most children probably have at least one of those things.
Exactly. Inclusive and true. And finally, a rectangle is a quadrilateral or a five-sided polygon.
Well, it's got to be exclusive. A rectangle can't be both. And it's true because a rectangle is a quadrilateral.
You got it. So, even though the standard or in logic is inclusive, being aware of the context helps you figure out when it might be exclusive in everyday language. Okay, so we've covered and or, but the sources also talk about these special words or phrases called quantifiers. What are those all about?
Right. Quantifiers. They're essential for making more general claims or saying that certain mathematical objects exist.
Exactly. The two big ones we see all the time are there exists and for all, or sometimes you'll hear it as for every. There exists means there's at least one thing in a set that fits a certain description.
Like, there exists a rectangle whose all sides are equal. That's true because squares exist and they fit the bill.
Exactly. And for all, or for every, means that a property holds true for every single member of a set. Like, for every prime number p, p is an irrational number. That's a valid mathematical statement, but it happens to be false.
False because, well, there are prime numbers that are rational, like 2, 3, 5, and so on.
Precisely. And one of the coolest things the sources point out is how the order of these quantifiers can make a huge difference.
They give us this pair of statements to compare. The first one is, for every positive number x, there exists a positive number y, such that y is less than x.
Which is a true statement.
But if you switch the order of those quantifiers and say, there exists a positive number y, such that for every positive number x, we have y is less than x, it becomes false.
Right. The first statement says that no matter how small of a positive number you pick for x, you can always find an even smaller positive number y. That makes sense. There's no smallest positive number.
But the second one says that there's one specific positive number y that's smaller than all other positive numbers. That's just not possible.
You got it. So the order of those little phrases, there exists and for all, completely changes the meaning and the truth of the statement. It's amazing how much power these seemingly simple words have in the world of math. Just to be super clear, remember and or, those are our connectives. They join statements together.
And there exists, and for all, those are our quantifiers. They tell us how widely a property applies.
You got it.
Okay, we've covered so much ground here. We talked about what makes something a legitimate mathematical statement, how to negate statements, how to build compound statements with and or, and the power of quantifiers like there exists and for all. I feel like my brain is doing logical gymnastics.
It's a lot to take in, but as you said at the very beginning, this isn't just about math class. Understanding these logical building blocks helps you think more clearly and critically in any area of life.
Absolutely. Whether you're prepping for a big meeting, trying to get a handle on a new subject, or just being curious about the world, knowing this stuff helps you avoid information overload and really understand what people are saying or trying to say.
It's about cutting through the noise and getting to the core of an argument.
So as you're reflecting on all this, our dear listener, I want to leave you with a little challenge. Start paying attention to how these principles of truth and falsity, of ands and ors, of for all and there exists, play out in the information you encounter every day.
In news articles, in online debates, in conversations with friends, everywhere. You'll be surprised how often these logical structures pop up.
Exactly. And once you start to see them, you'll be able to analyze arguments and claims with much more clarity. Are there hidden ors that are actually exclusive, changing the whole meaning? Are people making universal claims that you can easily disprove with a single counterexample? Start thinking like a logician, and you'll see the world in a whole new light.
That's a fantastic takeaway. And remember, this is just the tip of the iceberg when it comes to mathematical reasoning. In future deep dives, we can build on these foundational ideas and explore things like implications, proofs, and all sorts of other fascinating logical structures. The world of logic is vast and incredibly powerful.
I'm already looking forward to it. Thanks for joining us on this deep dive into the foundations of mathematical statements. Until next time.